In this small video, we're talking about analysing flotation data, but with a view to eventually, with the results, put it into a simulator. Previous to this, we had analysed flotation data and created a set of particle types. We're now going to use these particle types and get flotation rates. Now, this is the lab data flowchart. So it's just 4 flotation cells in sequence with the concentrate going to the next flotation cell. And so successively we're getting more concentrated particles. Now there are definitely issues about the way this information is used in the simulator. So it's more of a schematic, simplified methodology. It's not really the way you do it in practice. You'd want more detail. So here's the data, original data. The grades are from 0 to 1 rather than 0 to 100%. And this shows the mass flows. Now I've done it relative to 1 so that the original feed is simply 1. So normalize the data in some sense. And the scores here are based on principal component analysis. Now this, to some extent, won't make much sense unless you watch the earlier video on principal component analysis. The tails, the yellow, are all calculated using simple mass balance. Now, again, from the principal component analysis, we get particles. Now, there were actually 8 particles, and I've done some pre-analysis, and it turns out that particles 3 to 7 do not appear when I do the analysis, meaning the particles are fairly liberated. And you'll see the results and get an idea of why I've not included those in the model fitting. So these are the grades of each of the particles. So particle 1 is largely barren, particle 8 is largely liberated. Now I've used lead rather than galena, which would have been probably more physically realistic, but it hadn't been converted by the client to galena or sphalerite, and so I just decided to do this with the original element data. But I know that the limit for lead is 0.86. Now we want to calculate the distribution of the particles in each of the streams, the concentrate streams, the feed streams, and the tail stream. And it does become a mass balance problem. But it's an ill-posed mass balance problem, meaning there's multiple solutions. There's more unknowns than there is knowns. So because of that, we use a probabilistic approach. Now, this is an overview only, this course. If you do the course in depth, we will explain more about how probability theory is applied. But I'll flag the fact that it's not conventionally applied in mineral processing. So it's a unique capability of this methodology. And you'll already grasp that there's plenty of unique capabilities of the methodologies in the series of videos. So we consider the recovery as a probability. It's a probability a particle of type I goes to the concentrate. We use a probabilistic system, and because of that, it's a non-linear optimization problem. It's not simple. Well, we can try and use Excel solver, but it couldn't successfully handle the non-linear equations. But if you are interested in Excel solver in more depth, there's a course applying mass balancing using Excel solver. So these are the optimization, and it provides a distribution. We can use that and we get separation curves. So flotation recovery versus these principal component scores, which we can transform into a recovery curve versus the lead concentrate. And as I said, it's from 0 to 1. And this appears almost realistic. There would be a few concerns, particularly the way this goes up and then flattens off, but there isn't a lot of data. And given the information we have, this is actually reasonable, but we would certainly want more data to get a more accurate result. So flotation modeling can be applied using representative particles rather than floatability components. We could have done this using floatability components as well. I would suspect the results would be similar, But this is providing better interpretation because it's actually telling you that there's a lot of liberated particles. I did try it with the 8 particles originally, and many of those, when it came to the distributions, would give a small number of small distribution value in those particle types, so I eliminated them. And I haven't gone through the details of the whole calculation process here. In order to do the optimization, a new optimization system was created. Now, just to highlight, this optimization system can be applied to other problems, not just flotation. So we've made quite a few jumps in this series. We've gone to particle-based modelling. I would put to you that particle-based modelling provides a more accurate approach to modelling mineral processing than the more convenient floatability approach. And I've given courses over many years, and no researcher, and there's been professors who've gone to my courses, none of them have actually pursued this hypothesis. Now, this is a overview course only. If you want to do it in more depth, I'm preparing a Udemy online course. There are, of course, direct courses. And just flag that you're interested. And if I get more than 20, I'll present Udemy courses in more depth. I really appreciate your attention and look forward to your attendance at the 4th video where I will use this data to do simulation.